Yeah.
Any questions for that? Oh my God.
Yeah.
She says.
We talked about this business with, when you cite some more thing to. Okay, you, if you is algebraic, okay. Which is very convenient because it's much less difficult to think about things in these terms than in this. Give you an example. And I 14.1a. That you consider the real root of f of x is x5 minus 2. Right? I think we can all get behind the fact that the fifth root of 2 is some real number, is the root of this, right? By the way, this only has one real root. Anybody know how to prove that? Nothing fancy, just think calculus. Right? What's that prime of x? Notice the derivative of this is always greater than or equal to 0. So what does that tell you about the function f of x? It is always increasing. Everybody agree with that? So since it's always increasing, there's and two things. It's always increasing and it's continuous everywhere. Then that means that it can have at most one real root. The fifth root of 2 is one of the real roots. There you go. So this has four complex dropouts. Everybody okay with that? By the way, does anybody know how to find them? I think this might be a worthy, this is an algebra class after all, this might be a worthy exercise. Can you all write the roots of this explicitly in terms of radicals, or? So I'm going to call one of these roots the fifth root of 2. That's the real one. How am I going to get the complex conjugate ones?
You rotate it by 360 divided by 5.
That's essentially it. So a general root yes, it can be derived. So I'm going to use some basic complex numbers here. That's the equation that we're trying to get a solution of, right? I want you all to stop me if I do stuff that you haven't seen before, because this is going to be useful later. Notice e to the 2 pi I is, are y'all familiar with e to the I theta is cosine theta plus I sine theta. How many of you have seen this before? Where did you first see it? Oh, you saw a differential equation. You might have seen this first in a good trigonometry class, but not oftentimes trigonometry class don't get here. You can also derive this in Calc 2. Do you know how?
Oh, the series.
Yeah, that's right. That's what I was doing. Write down the series for this. E to the I theta is equal to the sum I theta n over n factorial How many of you have ever seen this? But I take it you have. Anybody else seen it? So let's do this. This is n equals 0. Let me just write the first few terms to kind of give us a feel. This is 1. This is plus I theta over 1. Now when you square this, you're now going to get minus theta squared over 2 factorial. When you cube it, you're going to get minus I theta cubed over 3 factorial. When you take the fourth power, out of the fourth is back to 1. Fifth power, minus sixth power, et cetera, et cetera. Now, here I'm liberally using the fact that this series will converge absolutely. I'm also playing a little fast and loose because I've got an I in there that they're not used to in real calculus. But what you get is 1 minus theta squared over 2 factorial plus theta 4 over 4 factorial minus theta 6 over 6 factorial, blah, blah, blah. And every other term has an I in it. This is theta minus theta cubed over 3 factorial plus theta 5 over 5 factorial. That should be a plus. Not bad. Minus theta 7 over 7 factorial, blah, blah, blah. Anybody recognize the series? It's a series for cosine theta. And this is a series for sine theta. So in particular, this gives rise to this interesting e to the I pi is equal to -1. That's e I pi equals cosine pi, which is -1. Or if you bring the -1 over, you get e to the I pi minus 1 equals 0. And I've heard it said that that's the best equation in math because it involves every interesting number, e I pi 1 and 0. So, but anyway, here, notice that this thing is periodic. Every 2 pi it repeats, right? Because e to the I 2 pi is just 1. So this allows me, oops. So you actually get a list of roots here. I should be doing about 2. What am I doing here? One, 2. Oh, that's right. This one's real. These two are complex conjugates, right? Because the real parts on these two are the same, and the complex parts vary by, or the imaginary parts vary by sign. And these two are complex conjugates.
So when you're trying to find like any group, you just set the equation equal to the const, or set the variables equal to the constants, and then times each I to the 2.
Yeah, because remember n is in z, right? So this could take any value to n equals 0, 1, 2, 3, 4, and then I quit. Because when I hit 5, I start to cycle over again, right?
Dr.
Yes,
You were saying that we could do it with,
radicals?
yeah, radicals.
Well, I mean. Uh, 2, 4, I forgot 6. What are the proofs of? And 1, actually.
X. With fifth minus one. So,
I agree with that. I'm most interested in these roots here. Right? One's easy. Notice one is the root of this one, so we would like to solve this. Any ideas?
good for it, take four.
I got a better idea. Back to this. Actually, I'm gonna assume a form like that. Because the two, there's 4 non-real complex roots of this, right? And they should come in constant pairs. So I'm gonna use the symmetry of the situation to assume a nice form like this. Okay. Let's multiply this out and see what we get. Let's see, this is going to be. By the way, somebody tell me why I should be encouraged at this point that this might work out well for me. Notice that, of course, all the coefficients have to be 1, right? Notice that automatically the cubic term and the linear term are the same, right? So that's encouraging. So I have to solve following equations. So this gives me alpha beta is equal to -1. which equals, I'm gonna replace beta by 1 minus alpha. And so this gives me alpha squared minus alpha minus 1 equals 0. So the alpha is 1 plus square root of 1, so it's 5 over 2. Now you might say, what about the plus or minus? Notice that whichever one I take, beta takes the other one. Notice when I add these two up, I get 1. And notice when I take the product of these two, I get negative 1. All right, so those are 2 solutions. Yes.
And we could do this for any, like, rotation?
Well, you can do it, it just might not work well.
Okay.
So, so my solutions are here, gamma can play the role of either alpha or beta. X is equal to negative gamma plus or minus the square root of gamma squared minus 4 over 2. So my solutions here are solutions to x4 plus x cubed plus x squared plus x equals 1. So these 4 weird roots of 1 are minus 1 plus radical 5 over 2 plus or minus the square root of and I can put a plus or minus there. So there they are in terms of radicals. You can simplify this a little bit if you like, and then multiply that by 2 to the 1/5, and that'll give you your roots. Right. Yes.
Where is the x squared plus gamma? X plus beta. Okay.
Well, I'm just being very lazy. This is just a shortcut notion for it. It can be either
Oh,
alpha
okay.
or beta here. Yes.
And then the square root term, big square root, is where you have your imaginary component.
Yeah, that's right. Because in either case, what you have here is this is whatever this is, 6 plus or minus 2 radical 5 over 4, right? Right, I did square that. So it's going to be 6 plus or minus 2 radical 5 over 4, and then you're going to subtract 4 from it. So it's going to be this radical. In any case, it's going to be negative under the radical. Any questions on that? But see, here's the point. I've got a little feel of what I want to do. Let Z be one of the non-real roots. Right. Well, the previous result from last time is that Q adjoined with U is isomorphic to QX mod the ideal generated by x to the 5th minus 2. Right? You remember that from the last time, because x to the fifth minus two is the minimal polynomial for you, or for you, right? Everybody go with that? But there's no difference between this and q z. Right, because the minimal polynomial for one of those non-real complex numbers is the same minimal polynomial. So notice, I find this a little bit interesting. These two fields are isomorphic. But this one is a subfield of the real numbers. Everything in here is real. And this is not a subfield of real numbers, because in fact, z itself is not a real number, right? Even though they are isomorphic. Okay, any questions on that?
Dr. Clinton, what was U again? U is a,
The real fifth root too. Yes, yes.
So anything that has a real and complex root can be isomorphic to the field. with
Right,
them.
so here's the big takeaway. This thing has 5 roots, right? 5 roots, one of them's real, and then there's 2 paracomplex conjugates. It doesn't matter which 2 roots you pick, Q would join with any 2 roots, they're isomorphic, which is kind of cool. Of course, that polynomial being the minimal irreducible polynomial for those elements is important. Theorem 1419. Let's suppose that we have an isomorphism of fields. Suppose we have an isomorphism of fields. U is in an extension field of K, and B is in an extension field of L. Then the original isomorphism extends to an isomorphism of K U adjoined LV. We can extend the to an isomorphism. That's what I call it. Star from KU LB if and only if one of the following do first condition U is transcendental over K, and B is transcendental over L. Okay, so easy enough. They're both transcendental, you can make it work. On the other hand, U yeah. I need this. I need to state my signal more carefully. U is the root of the irreducible polynomial. I didn't say that in the notes. F of X, K of X, and V is a root of tornado F of X and L of X. Okay, let's do a quick proof of this. The first case is easy enough to show. By the way, and let me clarify something first. What do I mean by tornado of FX? Well, and K of X is this way. Then tornado F of X is so it's just you just take every coefficient of F of X to the corresponding thing. It should go to an L. Everybody okay with that? All right. Let's suppose that suppose we have an isomorphism here. And when I say this, and I wanted to say B star of U equals B. Suppose we have an isomorphism from here to here, such that B star of U equals B, and B star restricted down to K is equal to whatever that Greek letter is. Number one, or if U is transcendental, then so is B. And conversely, because if V is algebraic, then B is a root of G of X and L of X. If G of X is B0 plus B1X plus Bn Xn, then F of X is equal to has U as a root. Right. So in other words, if V is a root over here, this means that B0 plus B1V plus Bn Bn is equal to 0. But if I apply the inverse, I get inverse E2 U squared inverse E n U n 0 and U is algebraic over K. The converse of this is almost the same. That is, if V is transcendental, U is transcendental. Okay. What if U is the root of the irreducible polynomial? Well, the proof of this is very similar to that. It's the same idea. So what we have is, on the other hand, if U is a root of x, which is A0 plus A1x plus ANXN, then this means that 0 is A0 plus A1U plus A2U squared plus ANUN. Now apply our isomorphism here. 0 is and this is equal to, notice when I restrict this down to elements of K, I get the original, and this applied to U is V. V. Therefore, V is root of that. As predicted. How about the other direction? So suppose we have condition 1. Suppose both U and V are transcendental. Then why does this extend to a isomorphism? Well, here's what happens here. So for the other direction, let's suppose that is transcendental over K and B is transcendental over L. Well, if you look at KU, this is isomorphic to KX. Where here X, I mean an indeterminate, right? That was one of our big things about transcendental elements, is when you enjoy a transcendental element, it's the same as rational functions. But K and L, my hypothesis, were isomorphic fields. So rational functions over K is isomorphic to rational functions over L. And the isomorphism is just basically use your tornado to take the coefficients of K with the coefficients of L in the rational function, right? And this is isomorphic to LV. And there you go. Just compose that once, twice, thrice, and that'll be your isomorphism. What about if they're algebraic? U is the root of the irreducible f of x, and B is the root of tornado f of x. So here's what we have. We have K algebraic case let's suppose, well, we have the K of U is isomorphic to Kx mod f of x, which is isomorphic to Lx mod tornado fx. Because again, these two are isomorphic, and the tornado takes everything in K, things in L, and takes f of x to this, and this is isomorphic to L. And again, do the compositions to get your isomorphism. Okay, any questions on
I have a question.
that? Mm-hmm.
So wait, in the part you suppose that U is transcendental over K and V is transcendental over L, you have that those are isomorphism by the up in here. How do you know that that isomorphism is the extension of the one you had to start with? Like, you know.
Oh, right. This isomorphism works just like when we did the earlier proof, just
Right.
replace U by X, right? And same here, right? So the real question is this bridge, is that correct?
Yeah.
Okay, so, here's why the bridge works, the middle one. What you know is you know that that little tornado guy takes, is an isomorphism from K onto L. And so here's what you do. Here's the nitty gritty of the way this works here. We'll call this middle one pitchfork. Well, pitchfork goes from so a typical element that's just a quotient polynomials, right? So I might write this as A0 plus A1 x, A n x n, B0 plus B1 x plus Bm x. And my only caveat is that that polynomial on the bottom just can't be the zero polynomial. And this is the way this works. Okay, my input was a rational function with coefficients in K. My output is a rational function with coefficients in L, right? And let's see, I guess it's fairly easy to show that this is actually a homomorphism just because of the way you add and compose this. Actually, I believe last time I started off by doing polynomials and extended to rational functions, but are you okay with this being a homomorphism? And it's 1-to-1 because X is transcendental over equals. And it's onto because the little tornado guy was onto L. Yes.
Why does the tornado take X to X, but it takes U to?
Oh, that's the way we define it, right? We're because X is like a variable. We're leaving that alone. So what we want an input polynomial, polynomial or rational function from K. We want its output to be polynomial rational function with coefficients in L. Right, and so we leave the X alone.
Okay.
Other questions? Okay. All right, so I'll give you that. Let me give you a quick example. This is in the spirit of the one that we did before, but I think it's quite worth seeing. So by the way, anybody know the significance of this number? Don't worry, it's not too complex. It is actually the primitive cube root of 1. So if you cube this number, you will get 1. Just for fun, do it, right? But this is actually, it cubes to 1 and no lower power. So actually, one solution to omega cubed is 1 is 1. If you divide out by that solution, you get this. So actually, this is, you can check the quadratic form, it matches this, right? This is the primitive cube root of 1. If you look at q adjoined with the cube root of 2, q omega cube root of 2, that is the smallest field that, this is a real field, right? It's the smallest field that contains all the rationals and the real cube root of 2. Contains all the rationals and omega cube root of 2. Or this one, by the way, in this case, the square of omega is a familiar name, it's the complex conjugate. Notice these three fields actually are distinct. It's pretty clear that this one is distinct from these two here, because these two have complex elements in them that are not real. This is all real. The fact that these two are different is also not too difficult, but it's not, it's blatantly obvious, right? But they are in fact different. These fields are all isomorphic because these three things, cube root of 2, omega cube root of 2, and omega bar cube root of 2, are the three roots of, anybody know what the polynomial is?
It's omega cubed times 1.
No, it's x cubed, sorry, it's 2. Roots of that, right? So you were right in spirit, sort of. All three of these fields are isomorphic. They're all distinct. Only one of them is real. And the intersection of these three fields is the rational numbers. The only thing that's in all three of these is the rational numbers. Here is does anybody see an automorphism? Or not, I'm sorry. Does anybody see an isomorphism that takes this one to this one? There is a map, there is a function that you may have encountered in other classes that gives you an isomorphism from q omega cube root of 2 into q omega squared cube root of 2. Anybody know what it is? Yes.
Can you not just replace every cube root of 2 with omega squared cube root of 2?
No, I want to go between the second and the third. Omega cube root of 2,
Oh.
omega squared cube root of 2. But in essence, we're going to discover that your idea does kind of work out in a certain sense. How about complex conjugation? Is everybody familiar with complex conjugation? It's map the complex numbers. It's 1-to-1 and onto, right? And in fact, when you restrict complex conjugation down to this, it will take this thing to this right here. Okay. Let me give you the following theorem. Let K be a field. Let K be a field and F polynomial degree n. And F of x in Kx degree n. Then, then there's a simple extension field such as the following hold. Such that, number one, there exists some u and f such that f of u equals 0. Two, the degree of ku over k Okay, so let me kind of talk you through this as we're going along. So you've got some field that you encounter on the street and some other polynomial, some of degree n. So we're going to assume it's not the zero polynomial. Then I can find a simple extension ku over k such as the following whole. There's some u and f such that f of u is 0. So yeah. Number two, ku, the degree of ku over k is less than or equal to n. And equality holds. If and only if. Anybody want to take a stab at what we need for equality? Something about the polynomial. If and only if f of x is irreducible. If f is irreducible in kx, then ku is unique up to k isomorphism. If f of x is irreducible, then f is unique up to k isomorphism. That means a field isomorphism that fixes k. So any isomorphism that leaves k alone. And k of u is called the field obtained by joining the root of f to u. In this case, f equals k of u is called the field obtained by joining the root of f. Okay, so why do we need irreducible here in our definition? Let me just give you a quick example. So here's an example here. Let's look K. Q, number one, f of x equal x squared minus 2. Then in this case, f is q joined with the square root of 2. And this turns out to be a plus b radical 2, where a and b are in q. Number two, if f of x is x times x plus 1, then if you join any root to this, notice the roots of this are 0 and minus 1. They're already in Q. right? Notice this is a degree 2 polynomial and the extension is only degree 1, because there was nothing new there. All right, everybody agree with that? And number 3, this is why we need irreducibility as well. If you have f of x is x squared minus 2, x squared minus 3, then here there's 4 roots of this, but you might pick this one, and this is not isomorphic to q squared root of 3. So when it's not irreducible, you still might be able to join roots, but you have to be careful and specify which one you're doing, because this has 2 reducible pieces, and taking the root of those 2 give you different field extensions. I think that's enough for today. Any questions? Any questions? All right. Well, I will see you folks on Wednesday.
Is it feel? Oh, it's the same as a regular.
Yeah, I say a K homework.